How's everybody doing today? Today we are going to look at the experiment number 8 in Labflow, which is constant pressure calorimetry. One important aspect of chemistry is the study of the energy involved in chemical reactions. For example, hand warmers. I used to live in colder weather and I used to run marathons, and I always had to use hand warmers. Hand warmers involve a chemical reaction between iron and oxygen to produce iron oxide. But we are not interested in the product iron oxide. We are interested in the heat that reaction produces. So thermochemistry is the study of the energy involved in chemical reactions. It is, I know it is, we cannot hold the heat in our hands, but we can feel it. We can feel the sunshine or the wind. And calorimetry is the study, is the measurement of the heat. And calorimeter is what we are going to use today, is a device to measure the heat. So today's objective is to be familiar with a calorimeter, basically a coffee cup calorimeter. And we are going to do 3 different processes and calculate the heat and measure actually the heat involved. One process is a neutralization. You are going to mix an acid and a base, and you know that it produces a salt and water and heat. And we are going to measure how much heat is involved in that neutralization reaction. The second process that we are going to measure is when you dissolve a salt in water. Involves a transfer of energy. Sometimes it absorbs heat, sometimes it releases heat. So we are going to measure that. And when the heat is measured at constant pressure, we call it enthalpy of solution. We are going to measure the heat that is produced when that salt is dissolved per mole of salt that we dissolved. And in the last part of the report is the measurement of the specific heat of a metal. We are going to go over what is the specific heat. That each substance has a different specific heat. It's characteristic of the substance. What is specific heat? It's the amount of heat that you need to add to 1 gram of substance to raise the temperature in 1 degree Celsius. And it's going to be different, as I said, for each substance. Water is the liquid that has the highest specific heat, and we will go over that. So as we do every week, I will give you a quick overview of the experiment. Then we'll do jointly problems that are related, but I want to make sure you know how to solve them. And towards the end, we will go over the report to make sure you know how to complete each section of the report. So let's get started by sharing the page of the experiment. Okay, so let's go over to make sure we know each part that is going to be in the introduction. That is going to be very helpful when we have to do the report and understand thermochemistry and do the problems and the pre-lab quiz. So the first thing that is talking here is about endothermic and exothermic reaction. You have seen that in lecture. When you have a process and heat is released, the reaction is exothermic and it feels warmer on the outside. Where heat is absorbed, the reaction is endothermic and it feels colder on the outside. And also, you know, I'm sure by studying your lectures, that if it's an exothermic reaction, what is the sign of the value? If it's an exothermic reaction, it means heat is released. And the system doesn't want to release anything. That's how I remember. So it's going to be negative, right?
Yes.
Yes, Douglas. Thank you. Exactly. And that is how I remember. I remember these rules that even if it's work of its heat, if the system receives something, is positive. And if the system releases something, it's going to be negative. So for an exothermic, it's going to be negative. Okay, what else is here in the introduction? When the heat, they're talking about when the heat of the reaction is performed at constant pressure, then it's equal to enthalpy change. We know that as well. And we call it delta H. And then what else they're giving us in the introduction? The units. What are the units that we use? Usually we use, there are three different ones. Basically, calories is the amount of heat that we need to raise the temperature of water in 1 degree Celsius. So 1 calorie is the amount of heat that we need in order to raise the temperature of water in 1 degree. 1 kilo, basically 1,000 calories is 1 kilocalorie. That's another unit. So let me see here. They're saying 1 calorie, they're talking about units, and then 1 kilocalorie, and then another joule, which is the international unit, is the joule. And that's something you probably need to remember if they don't give you that in the test. 1 calorie equals 4.184 joules. These are basically the units that you are going to use. What else they are talking about here? Calorimetry, as we already said, is the study of the heat transfer in a chemical reaction. And the calorimeter is the device that we use in order to measure the heat. So what is, what is heat? This is just to give you a little background that is not here. But basically heat, because it's hard for some students to grab that concept. What is heat? Heat is energy. It's the transfer of thermal energy. It's kinetic energy. a transfer between two bodies that are at different temperatures. So that is easier to remember when you think about heat. Another important aspect of heat is that always flows from warmer object to a cooler object. And the temperature is a measure of the thermal energy. So in our calorimeter, we are going to trust that we are going to have a thermometer that is going to measure the change in temperature. So if you have a reaction in a calorimeter and the temperature increases, then it's an exothermic reaction, releases heat. But for an endothermic reaction, the temperature of the calorimeter will decrease. And then here they are giving us a different equation here. I think this is a little confusing for you will decide how to use it. I believe this is a little confusing for the coffee cup calorimeter. But we'll go over because we'll do some practice problems and I will make sure that this is clear. But this is very important. The heat of the reaction, basically the heat that the reaction, whatever you have in the neutralization reaction, it is exactly the same as the heat that the solution absorbs. The only difference is the sign. If one releases heat, it has a sign, let's say negative, and the other one absorbed is going to be positive. So we are assuming that a calorimeter is insulated, so the heat doesn't go outside. So all the heat that the reaction is going to transfer to the solution in the calorimeter is going to be absorbed. The value is the same, just the sign is the opposite sign. And then we are going to use that the heat is going to be, the heat transfer is going to be equal the mass times the specific heat times the delta. I think this is better. This is also important. It doesn't the mass, but it's basically when you are given the specific heat of the calorimeter. Because if you want to go a little bit strict, but it's not for a coffee cup calorimeter, it's another kind of calorimeter, you can say that the heat of the reaction equals the heat that the solution absorbs plus the heat that the calorimeter absorbs. In this case, with the coffee cup calorimeter, we are not going to assume that the calorimeter absorbs anything. So all the heat from the process is going to be absorbed by the solution. And the formula is going to be this. Delta T is the final temperature minus the initial temperature. So the important thing is that the heat of the reaction that is absorbed by the solution in the calorimeter is going to have opposite signs. Any questions so far? Okay, so then let's continue. Here, okay, awesome. So let's continue here with what they are telling us. Here they are adding the mass of the solution times the specific heat of the water. So at the end of the day, they're using the formula that I gave before. And then what they are teaching us here is that the mass is in grams, and when we say we mix 50 milliliters of water, we need to assume that the density is 1, so 50 milliliters is going to be 50 grams. But we'll see that when we do some practice problems. So they're talking about that the volume of the solution in mLs is equal to the mass of the solution. And then basically they're giving us this equation that we are going to use. The heat of the reaction, whatever we are doing, A, B, or C, is going to be minus the heat that was absorbed in the calorimeter. And because we don't consider how much heat was lost or absorbed by the calorimeter, we are assuming that the heat of the reaction is going to be absorbed by the water or the solution that was inside the calorimeter. And the only difference is the sign. And that's how we calculate the heat of a reaction, by measuring how much grams of solution are in the calorimeter, the specific heat of water that we know, and the delta T. Delta T is the final temperature minus the initial temperature. So the final temperature is going to be the temperature once the reaction is complete. You wait until everything stabilizes and you measure the temperature in the calorimeter. And then the initial temperature is the temperature of the solution before the reaction occurs. And then they're talking about how all of the three processes that we are doing. The first one, heat of neutralization. So we will study the transfer of heat for the following acid-base neutralization reaction. It is this one. Hydrochloric acid, we are going to mix with sodium hydroxide to produce salt and water, sodium chloride and water. And here, what they are saying is that since hydrochloric acid and sodium hydroxide are strong electrolytes, then obviously the sodiums are spectators, and this is basically the net ionic equation for an ionization. And then we are going to calculate, they are going to ask to calculate the enthalpy of neutralization. And how are we going to do that? First, we are going to go over that, but first we know that the heat of that reaction equals minus the heat absorbed by the solution. And once we have that, we are going to divide by the moles that reacted. In our case, we have to look, we have a chemical reaction, hydrochloric acid that reacts with sodium hydroxide. So we have to look which one of these two is our limited reagent. But in our case, as is written in the procedure, they have equal amount, so we don't have to worry. We can use any, but they ask per mole of hydrochloric acid. So all we have to do is calculate the number of moles. We have the concentration of the hydrochloric acid, and we have the volume of the hydrochloric acid. So if we multiply the both, we're going to have the moles of hydrochloric acid that reacted. We'll go over later, but this is just something in advance. And then the B part, we are going to calculate the enthalpy of solutions of salt. So when a salt dissolves in water, it's a transfer of heat. And that, at constant pressure, that heat transferred is called enthalpy of solution, delta H. So that's what we are going to calculate. First, we have to calculate the Q. The same way we do it before, with the same formula, that Q equals M C delta T. But the mass that you are going to include is the whole mass of the solution. So you have to include, we'll go over that, the mass of the salt plus the mass of the solution. And then once you have this Q of the reaction, you are going to divide by the moles of the salt. When you dissolve in water a salt, some salts absorb heat and some other salts release heat. So we are going to see that. We're going to give you two different kinds of salts, calculate the enthalpy of solution. And the last part, here they are talking about that. Heat may be given off or absorbed by the salt as it dissolves as ions in water. This is exactly what we just said. And then the last part of the report is to calculate the specific heat of a metal. We are going to, what they are saying is, if you have water in a calorimeter, and then, let me see if I have a drawing here. I added this drawing. So this is the calorimeter, very simple. What is, there are two styrofoam caps right here. 1 and 2. Basically, the objective is to isolate it so we don't lose any heat. What else? We have the thermometer here, and this is a stirrer. We want to make sure that we mix everything well, and when we measure the temperature is the right one. It's homogeneous. So basically, we are going to have a solution here inside the calorimeter, and we are going to measure the temperature of that solution. And then we are going to add a piece of metal that we know how much metal we have. And we know we put that metal in boiling water, so it's very, very hot. We know the temperature of the metal when it's hot. That will be the initial temperature of the metal. And we are going to drop that in the water inside the calorimeter. We are going to wait until everything stabilizes, and that way we are going to take the final temperature when everything goes to equilibrium. But we know that the heat flows from higher temperature to lower temperature. So the metal is going to transfer heat to the water. So the temperature of the water is going to raise, and the temperature of the metal is going to go down. And when everything is in equilibrium, we can use this equation to calculate the specific heat of the metal. So they started here. Now that we know how the process works, the first thing they are saying is the heat that the metal lost equals minus the heat that the water absorbs. Does it make sense? This is important. This is where we start. Once we know that, we write the equations. What is the heat of the metal? We always use the same equation. C times M times delta T. The delta T of the metal, we know. We know the final temperature. At equilibrium, we know the initial temperature of the metal. Mass of the metal, we know. And this is what we know, the specific heat of the metal, how much heat I need to raise the temperature of that metal in one gram of metal in 1 degree Celsius. And on the other side, we have the heat that the water absorbs. We know the specific heat of water. We know how much water we added, and we know the water delta T. So that's how we are going to calculate the specific heat of the metal in the last part of the report. Any questions so far? Okay, so then we'll move to some practice problems that I consider those important for here to understand this experiment and also for lecture as well. So let's share some problems here. How is a calorie defined? Yes.
Is it a measure of energy?
I couldn't hear you, sorry.
I'm saying, is it an amount of energy?
Yes, it's the unit. Yes, exactly. It's a unit that we use to measure heat. And you know, we use meters to measure length. We use grams to measure weight or mass. And is one of the units that we use to express the heat, the amount of heat. And how do we define a calorie? Is the amount of heat that we need to raise the temperature of 1 gram of water by 1 degree Celsius. So that is a definition that is based. If then we have something else, we would base, because we are using calories, it's one unit, and then we base our measurement of heat in that calorie. So does it make any sense?
Yes, ma'am.
Okay. So basically, it is a unit. We can use calories, or sometimes another unit of heat is joule. Okay. Now, so because it's if I get if it kicks me out, stay and I will come back. Hopefully not, because it's showing me some weird notices and it's showing in red. Okay, so we said that an exothermic reaction is a reaction that releases heat. That's what you said. People remember like exo, they remember as exit. Many people do that. And they say exit. So the heat exits the system. So if a reaction is exothermic, releases heat and it feels hot. How does it feel on the outside? Hot, if it's exothermic. But if it's endothermic, it's the opposite. Endo basically absorbs heat and it feels cold on the outside. So those are questions that you might encounter. And then let's look at these problems. If you have a solid that dissolves in a solution and it feels cold on the outside, is it exothermic or is it endothermic?
Endothermic.
Yes, awesome. Endo. How about a reaction that has a negative Q? Is exo or is endo?
Does a Q stand for DH?
Yes, Q is the heat that when it's a constant pressure equals the enthalpy.
Okay, so I think it's exothermic then.
Yes, awesome, exo. Because the way I remember is that if it's negative, the system doesn't like it. And then it's because it's losing heat. But whatever works for you, as long as you remember, but it's exo, very good. How about the last one? Ice melts into
Ice melt.
liquid.
So that's an increase in temperature. So final minus initial. Endo.
Endo, yes, awesome. You have that as you just did it, final minus initial, that's a way of doing it. Also, if it's negative or it's positive, or if it feels cold on the outside, then it's endo. If they tell you if it's hot, then it's exo. So there are many different ways. And then I have two problems that I think you will need to, these are actually problems that are at the end of the write-up. Have you seen those?
No, I haven't read the.
Okay, so those are at the end, and I want to make sure that everybody knows how to solve those. So there are three actually, and I will solve today two. So let's look at this problem. You have a calorimeter, and it says that 200 mLs of hydrochloric acid, I give you the concentration, is mixed with 200 mLs of a strong base in a coffee cup calorimeter. And the temperature of the solution increases from 21.35 to 27.05. And they give you the specific heat of the solution, which is the same as the water, and assume that when they tell you the density of each solution to be 1 is because they want you to convert these mLs into grams. But if the density is 1, 200 mLs of hydrochloric acid is going to be equal to 200 grams. And they ask you what is the heat of reaction in kilojoules per mole. So where do we start? When you see a calorimeter, then you say, okay, calorimeter, I'm sure I have to use this formula, M times C times delta T. I'm sure you will just say, in the calorimeter is not much we can do. So here is the reaction. First, you have to have the balanced equation. And what they are telling you is that the temperature increases. So is this reaction exothermic or endothermic? The neutralization, when you mix an acid and a base, is it exo or is it endo?
It's exo.
Yes, exactly. That means that here you have heat. Exactly, it releases heat. They don't write it, they care about the products. But here in this chapter, we care about the energy as well. Energy is very important. We are nothing without energy. And many of those energy resources that we use every day are chemical resources. So it is an important chapter. It's just difficult to grab because we cannot hold the heat in our hands, and it's a difficult concept to grab. But okay, once you get used to, how are we going to calculate the heat of the reaction? What do we know? The most important, we have the calorimeter, right? And we know that the heat of the reaction, this heat that was released here when the reaction was done, is going to be equal minus, because it's opposite sign, so this is key, the heat absorbed by the solution. This is very, very important. Does it make sense so far? So then, because we know this, the heat of the reaction is minus the heat absorbed by the solution, we know this formula of the solution. It's minus the mass, the grams of the solution, times the specific heat of the solution, times the delta T, which is this formula. So with that, it's going to be really easy to solve this problem. So what is the mass of the solution? Because we have to know mass, specific heat, and delta T. How do we calculate? And then we will have the heat of the reaction. And the last part will be divided by the number of moles. But let's go step by step. So for now, we are calculating the heat of the reaction. But they are asking what is the heat of the reaction in kilojoules per mole. So once we have the heat, we have to divide by the moles. And now we are calculating the heat of the reaction. So you can tell me, what is the mass of the solution?
200 grams.
200 grams of hydrochloric acid plus that is mixed with 200 grams of the solution of barium hydroxide. You have to consider everything that is inside the calorimeter. So the total volume that you have, even though you mix both, you have to consider that immediately when you mix it, the volume of the solution is 400 mLs. So what would be the mass?
400 grams.
Exactly. Very good. What is the specific heat? It's given here.
4.18.
Yes, very good. Joules. Always write the units just to make sure. And what is the delta T? Final minus initial. What do you get when you do that?
5.7.
Very good, yay. 5.7, awesome. So when you multiply 400 times 4.18 plus 5.7 Celsius, this cancels with this, grams cancel with grams, and your units are going to be in joules. So when you do that calculation, the calculator will tell you 95, I got 30.4, and always look at the unit. The Q, the heat, always will have units of calories or joules, depends on how they are giving you the C. The C here is in joules per grams per Celsius. So your units are going to be joules. Very good. But they don't want me to stop there. They want the heat, the heat of the reaction in kilojoules. So basically kilojoules, I have to divide by 1,000. 1,000 joules is 1 kilojoules. But they want it in kilojoules per mole. So I have to calculate per mole of hydrochloric acid, or the mole. I don't think they're going to give you that hard of a problem, but you have to use the limited reagent. So you basically have to calculate how many moles of this you have and how many moles of barium hydroxide you have, and use a limiting reagent. But in this case, they don't want to bother you that much. So how do we calculate the number of moles of hydrochloric acid? You know that the moles is always concentration, molarity, times the volume in liter. And the molarity, they're giving us the molarity 0.862 moles per liter. Times, what is the volume in liter?
0.2.
Very good. So what I get is 0.1724 moles. In theory, you have to use the one that is your limiting reaction. You have to do the same for barium hydroxide and use the one that you have less, all the one that was involved in the reaction. But here, both are involved the same way. You don't have excess. So now we have, what do we have? We have the number of moles of hydrochloric acid, and we have the Q. So what they want is basically, they want the Q divided by the moles. That's all they want. Because they are saying heat of reaction in kilojoules per mole. So all we have to do is 9530.4 divided by 0.1724, and this is actually joules, and this is moles. But I will get a number that is 55278 joules per mole. But because they want it in kilojoules, I divided. I move the 3 places. So the answer is 55.3 kilojoules per mole. Do you have any questions for this one?
Yes.
Okay.
Like up there on Q is equals to mass times specific heat capacity times heat change. There was a negative behind M solution. Why did we use it?
Okay, very good. Very, very good. So what is the delta T? Is it positive or is it negative?
So 27.05 minus 21, it becomes positive.
Positive. So actually, you caught me, because this should be negative. I missed it. Let me double check because I missed it. I'm glad you caught it. Let me check here because I think they give you the solutions, I believe. Let me see. I think they don't tell you how to do it, but I think they give you the answer. Yes, the answer is negative. Okay, I'm so happy. So you were right. I lost it on the way. So the answer is negative. And look at this. It makes absolute sense. When the heat is negative, it is lower than 0, means the reaction is exothermic. It lost energy. So everything makes sense. Sometimes this delta T is negative, and then with the minus, it changes. But yeah, don't do what I did. Don't lose that minus. Awesome. Any questions there?
Also on the formula, I'm a little bit confused. Like there's this formula where you say the Q of the reaction is equals to negative Q of the solution.
Here.
So does that same formula mean the one on the right side, or is a different one? Because I was confused right there.
Right. What it says in this one is that they have opposite signs.
Okay.
And we know by the temperature they have, so we are calculating the Q of the reaction, and it's going to have the opposite sign because the reaction released energy and the solution absorbs the energy. So we need the minus here.
Okay.
That's all. And then it's minus, and then we write what is the Q of the solution. That is the mass of the solutions times the C times the delta T.
Okay. Because like on the temperature change at 27.05 minus 21.35, it is positive. So that one means is a Q of the reaction.
That means that the solution, because it's positive, absorbs the energy. Because the temperature increases, the solution absorbs, but the reaction releases.
Okay, so is that heat of the system or is it the heat of the surrounding?
No surroundings. It's all our system. Our system is all inside the calorimeter.
Okay.
So basically there is a chemical reaction inside the calorimeter and is transferring all that heat into the solution.
Okay.
Our system is the calorimeter.
Because the final minus initial, if it's positive, that means the reaction is
Not the reaction, because final minus initial from the solution. So you have a chemical reaction that is giving heat to the solution. The reaction lost heat. That's why we needed that minus, actually. So the solution increases from 21 to 27. So the solution increases the temperature, which means that the solution absorbs energy, which means that the reaction lost energy.
it's a little bit confusing.
It is confusing, I have to tell you, because what we think is of that everything is the same, basically. But
Yeah,
you can think in a different way. You can think that you have water.
Yes.
And then the water, because actually we are treating it as water. And you can think of the reaction as just the mixture of the moles of solid hydrochloric acid that mix with solid barium hydroxide. You can think of that. So you mix those solids, and when you mix them, they transfer the heat to the water. And then you can divide a little bit that, but it's confusing. What is important is that the water absorbs the heat that was released when the hydrochloric acid mixed with the base, with the acid mixed with the base. You can think of solids, and so you can separate the solids that produce that heat and the water that absorbs that heat. Does it make more sense? Or
Yeah, I'm here.
yeah, okay. So does it make more sense? Or what is important, I would say, is to know that the heat of the reaction, which is the mixture of the acid and the base, is released to the solution. You can think of water. You can think that when the solid mix, they release to the water, and they have opposite signs. And we are going to calculate the heat by using, all we have is the water, the solution. We have 400 mLs or 400 grams of water. We calculate based on how much water was absorbed. And then we change the sign here, and that's how we end up calculating the heat of the reaction.
Okay, so do we have some examples where the temperature drops or decreases?
Yes, I think in the report there is one, I think.
Yeah, I really wish to
Yeah.
see how we do that.
Okay. So neutralization is going to be like that. It's going to release heat.
Okay.
So you have to have the negative here. I'm glad you got it. So let's look at one more example here and see how it goes. This one is not a neutralization as we did before. Let's read the problem. We have 9.96 grams of a salt, lithium chloride, and we dissolved that in 100 mLs of water. When you dissolve a salt in water, sometimes it releases heat and sometimes it absorbs heat. So they are asking is calculate the molar enthalpy. Molar enthalpy. We always, when you have a calorimeter, you are going to use that formula. And what is the molar enthalpy? Again, when you see molar, okay, it's going to be the heat released divided by the number of moles of lithium chloride. So all is happening in this problem is that you have 9.96 grams of a salt, lithium chloride, and you put it inside the water in a calorimeter. And then you want to know how much heat is transferred per mole of salt. So always, the first thing you have to do, calculate the heat. The heat is always going to be the heat that we use, again, the same thing. The heat of the reaction is going to be minus the heat of the solution. How much? Whatever the process of dissolving releases, whatever heat or absorbs, is going to be the opposite sign for the solution. And then it's going to be minus M times C times delta T. Now, what is M? If you read the problem, what is the mass of the whole system, the entire mass?
Is it 100 grams of water, and you add 9.96?
Yes, exactly. Don't forget, exactly. That is important.
Okay.
So the total mass, very good. 100 plus 9.96. The C, what is C?
C, they gave us is 4.18 joules
Yes,
per
very
gram.
good. Yes. Joules per gram per Celsius. What is delta T?
So it's 41.3 minus 22.2.
Yes. Very good. So what is the 41.3 minus 22.2? Okay. So what number do you get? This time I won't forget this minus. So what is the heat of the reaction? Did you get the same number?
So are we getting in joules or in kilojoules?
In joules, for now I did it in joules, but I think we have to change it because they wanted, yeah, in kilojoules per mole. They don't say though, but yeah. So now that we have the heat of the reaction, what do we need to calculate?
Now we need to calculate the number of moles of lithium in.
Exactly. How do we do that?
So it's the mass of the lithium divided by the molar mass?
Yes. Awesome. So what do you get? 9.96 times 1 mole of lithium is 42.394. How many moles did you get?
Mm, 0.235.
Same as me. Perfect. So the last part is the easiest part because they are asking molar enthalpy. Okay, so they are asking about the heat divided by the moles. So when you do that calculation, this number divided by the moles, I get minus 37.4 kilojoules. You get the same?
Yes.
Okay, so this is how we approach. In these problems of dissolution, keep in mind that the mass is the total mass. Don't forget to add the is for the one when you dissolve. And remember always this, that if one absorbs, the solution absorbs, the other release. And I guess, and the formula, obviously, and I think you'll be fine. Probably practice a little more. There is one more that you can try to do. And then I would like to go to the report to make sure that that all the steps are clear on how to do the report. When is the report due? Okay. When is this report due? Can you hear me?
Yeah, I can hear you now. I didn't get.
There is something wrong. Did you hear all the other part, or?
The last one I had is when you were asking when the report is due.
Okay, so we are good. Somehow the connection today is really bad. So when is due the report?
I'm not really sure, but usually it's due on Mondays.
Okay, because I had to add one more. I will do Monday. I will do the next one because the students are telling me that after the midterm, I was getting behind. So that's why I added this one.
Okay.
Okay, so this is the report. The first thing that you are going to see is whatever is in red means they are telling you. So the first part, they give you everything, the volume, they do it in duplicate. So the volume of hydrochloric acid, the temperature of hydrochloric acid, the volume and the temperature, and whatever is in red is given. So they give you the B part, and then when you are going to calculate the specific heat of a metal, they give you everything as well. And let me see. Okay, so now is where it starts, the part that you have to complete. So the first thing is here. This is the first part, A, the heat of neutralization. So what are you going to add in temperature difference? What is the temperature difference for sample 1? What do you get?
Volume, temperature 24, 31. So 31 minus 24.
Yes, perfect.
7.0.
Exactly. You will probably have different data, but I would just want to make sure that you know what. And then here, number of calories evolved. Enter a positive value. So here they want to avoid a positive value. What if you do it? What do you get? How are you going to do it? What is the mass?
The mass of, let me see.
That you use in the formula, because you are going to use Q equals, when they ask calories evolved, mass times C times delta T. So you will need to know the mass. What is the mass?
So we have a mass of the metal, and we have, so it should be 26 minus 19.711. Then what you get?
Because in order to get the mass, first you know that in this reaction, you mix hydrochloric acid and sodium hydroxide. You need to know that. But because they're giving you in milliliters, you have to convert into grams.
Okay.
But the density is considered 1. So the milliliter, 1 milliliter equals 1 gram.
Okay.
So the total mass is going to be the mass of hydrochloric acid plus the mass of sodium hydroxide. So what would that be?
99.9.
Okay, perfect. Yes. Okay, so we know. So you did a 50.1 plus 49.8, right?
Yes, ma'am.
Okay, awesome. So we have the mass. The C is easy. What is the C?
There's a difference between.
The C is a constant. The C is they will give it to you. It's the specific heat. In this case, is for water or for the solution.
4.1.
4.8 is if they want the Q in joules. If they want a Q in joules, you will put 4.18. But look what they are saying. Calories evolves in calories. So what is the specific heat for the water?
1 calorie is equals to.
Exactly. So this is 1 calorie per gram per Celsius. Very good. And what is the delta T? We already calculated here.
31.
7. Right.
Mm-hmm.
We have M, we have C, and we have delta T. So number of calories evolved, that's what you are going to calculate. In my case, but you are going to have different numbers, is 6.99.3 calories. And then they ask you how many moles of protons were neutralized. You know that you use, let's look at here. Here you have the volume of hydrochloric acid, 50.1. So the moles you calculated by 50.1 milliliters and you know the concentration. When you read in the write-up, in the procedure, what is the concentration of this acid, you know that is 1 mole, is 1 molar, 1 mole per liter. And then, because the liters and the milliliters don't cancel, you have to do the conversion. 1 liter equals 1,000 milliliters. But what is important here that you multiply the volume times concentration of the hydrochloric acid that you use in order to get the number of moles. Does it make sense?
Yes, ma'am.
Okay. And then the last, yeah.
Like, I think there's something you said about calculating the reducing reactants. You said something like that? Oh, we don't need it in this experiment.
That I said about what?
About reduce, like reducing, like the reactant, which is not enough. We have the
limited reaction. Yeah. Yes. What I basically said is that, let's say you have you mix and you have a lot of acid, but not all the acid was neutralized because you don't have enough base. So you only have to calculate the moles of the acid that were neutralized. But in this case, I would say make it simple and but you know what I'm saying? That the number of moles that were neutralized. So if you have that reaction of an acid plus a base, you look for a limited reagent. Basically you look at if all the acid was neutralized or there is some acid in excess.
Okay.
But in this case, you basically calculate, they don't give you excess. They calculate it, you don't have to do that.
Okay, got it.
Okay, and then the last part, the 7, how are you going to do it? It says calories evolved per mole of acid. So basically, you have the calories evolved.
Divide by.
Here I got 0.05 moles. And then when you do that, you get, I got for me, for 7, I got kind of, if I round it with the sig figs, I got this, 14,000. But because you have to write it in a different way, I think you have to write it 1.4. But you will have a different number though. What's important is that I wrote it this way. But so basically you divide the calories by the moles and that's it. So this is what you are going to do in part A. And then part B, let's see. We have to complete here. What number would you put there?
Mass of volume mass and volume. So 49.9 grams.
Exactly. No, the same, because it says
Yeah.
you have the volume of DI water. And they ask you for the mass of DI water.
So
It's going to be this. It's exactly the same. Because what they are saying is you have 1 ml, right, of water. Let's say, I say 1, whatever. And then the density is 1, which means 1 gram per milliliter. So what they are saying is the number is going to be the same, 1 gram. 1 ml is going to be exactly as 1 gram. So when you have to write mass of DI water, it's the same mass as the volume in milliliters. And then here you have to complete something else. The temperature difference. What is the
minus 21.2.
What is the difference? Minus final minus initial.
So
right? Did you get the same?
let me see. I'm doing it right now. 0.2. No, it's saying negative 2.98.
Okay, so you did temperature of mixture after dissolution, 21.2.
Yes, negative 3.
Ah, okay, awesome. And the initial is here. Okay, awesome. So that we know how to complete. Total mass in the reaction, total.
Total mass is so the mass of the salt plus the mass of the water.
Yes.
So let's see. 0.010. Yes, 51.91.
Awesome. And the last part, it says enthalpy of solution and in calories per mole. So first, we have to calculate the Q of the reaction. The Q, and
Is
then
mass.
divided by the number of moles. So how do we calculate the Q? Let's do it in two steps. In order to make 6, we have to do first the Q of the reaction. And then we'll divide it by the number of moles of salt. That is easy. We know the grams and we convert it. So how is going to be the Q calculated? It's going to be minus the Q of the reaction. It has minus the Q of the solution. So it's going to be again the same formula, the mass times the C. What is the mass?
51.91.
Very good. What is the C? Because they want calories. Look at the units. You say 1 calorie. If they want joules, you use the other one. They are equivalent. Times the delta T. What is the delta T?
-3.
-3. So this minus cancels with this minus. So our Q is going to be positive. And in my case, I got 155.7 calories. Because the grams cancel with the grams, the Celsius with the Celsius. But because they are asking for enthalpy per the enthalpy of solution, I have to divide by the number of moles of the salt. In our case is this. How do I calculate the number of moles of this salt? You have the grams here. It says mass of salt. So if you have the grams of salt, you just divide like the same way you did it before. Does it make sense?
So, like when you are calculating enthalpy of solution, how do you come up to say like you only calculate for the salts but not everything?
Okay. First, this is the Q of the reaction. Basically, how much heat was released in the calorimeter. But because people have to unify, if I do the experiment, in this case, they did the experiment with 2 grams of salt right here. 2 grams. Some other people will do it with 4 grams, and then the heat will be different, right? So they want to unify, and they want to tabulate those numbers so everybody can compare those. So then the definition basically of enthalpy of solution is the heat of the reaction. The heat of the reaction is a definition divided by the number of moles of salt. Okay. So then when you get a number, you can compare. In my case, let's say I got 6200 calories per mole. Because so this is what they are asking. And then we can compare, because if 1 mole of salt is going to release that amount of, or in this case, is going to absorb that amount of heat. Does it make sense?
Yeah.
Okay, so in order to calculate the Q, no, you have to calculate the whole thing because that's your experiment. So you are doing the whatever, how many grams you have in that calorimeter, you have to count all that. But then in order to express your result or your answer and to compare with the result of other people, everybody will say per mole. And that is kind of standard. So that's why, but that's only at the end. And then the last part is the specific heat that you have to complete. It will tell you which metal you have. And let me see, what do you have to complete? Here, they are asking you, let me see here. Okay, so they give you, in my case, I had zinc. They gave me the mass. Let's see. There is not much, just to calculate the specific heat in this one. Not much. So the first, you have to complete this and the mass of water. What is the mass of water that you're going to add? Let's look at the previous one. Look at the data here. What is the mass of water that you have in your calorimeter?
49.9.
Look at here. This is a different experiment. A, B, and C are three different ones.
Oh, so you are in C. Okay.
This is C. It's a different experiment. In the other experiment, in B, we calculate the enthalpy of solution. So there are three different experiments with three data. The first one was a neutralization reaction. The second was a enthalpy of solution. And this one is calculating the specific heat of a metal. So I think when you read the write-up, you will understand it better. So this one, the volume is 50.2 mLs they are using. So what is the mass that you have to complete? It will be the same number because the density is 1. So you're going to write the same thing. And then how are we going to calculate the specific heat? In this case, basically, you are putting a metal that is hot in the water. And you are going to know that basically the heat that the metal releases to the water when it's hot and you put it there inside the calorimeter is minus the heat that the solution absorbed. Do you see that so far?
Yes.
Okay, so this is important. So you put a metal that is hot in the solution, and the solution is going to absorb. And the signs are opposite. So this is really important. And then you know the formula for the metal. We always use the same formula. The mass of the metal times the C, specific heat of the metal, times delta T equals the mass of the solution times the C times the delta T. And what they want is for you to calculate the specific of the metal. So the specific heat of the metal is going to be the mass of the solution that you are given. In my case, what is the mass of the solution? Because the metal is solid, you are going to say 50.2. So the mass of the solution times the specific heat that you know is 1 calorie per gram per Celsius times the delta T, final minus initial, divided by these two, the mass of the metal times the delta T of the metal, that is going to be different than the delta T of the solution, because the initial temperature of the metal was hot, and the initial temperature of the water was a different temperature. Does it make sense?
Yeah, it's okay.
No? I think this is the formula that you will use for this part. And I think we are going to include this workshop, formal workshop for the people that then later come and watch it. And then I'll stay, and I would like to make sure that you are ready to do the report. And thank you.